Okay, so let's talk about the definition of mutually exclusive events. Another word for mutually exclusive is also the word disjoint. So, two events, A and C, are mutually exclusive or disjoint if they cannot occur at the same time. In other words, given events A and C, their intersection is empty. So this is another way of saying when we say their intersection is empty, that's how we would say it in a literal sense. But how we would say it mathematically as an expression would be something like this. Um, Commonly, you'll see a zero written like with an O and a line through it. Okay. And usually people use that to differentiate that between that and uh, the letter O in the English alphabet. Uh, but in the mathematics discipline, um, and in higher math, when you see an O with a diagonal line through it like this, this is actually referring to what's called an empty set. So, think of an empty set as like being a can of beans without the beans. It's just the container. And so the container would be this empty set symbol just to represent, a set that has nothing in it. So that would look something like this. Just the curly brackets that denote a set of things, but there's nothing between the curly brackets. Okay. Um, so I kind of went off on a tangent there. So again, mutually exclusive events or disjoint events is where the intersection of two events has nothing in common. It's empty. And because of that, the order of the intersection is zero. So the order of that intersection is zero. Remember, the order refers to counting. Okay. How many items or how many outcomes are in the intersection of those two events? So this is saying that there are zero outcomes that are in common between the two events. So here I'm kind of defining this, describing this mathematically, but visually, what does this look like? So here in this example, we've got two events, A and C, that are considered to be mutually exclusive or disjoint. And so you can see here on the left, we've got event A, which is everything inside those bounds. And then we've got event C, which is everything inside those bounds. And there is nothing in common between A and C because A and C, those two events, do not overlap. Um, so you can see here, because both of these events do not overlap, there's no items in the set of their intersection. And because there's no elements, no outcomes in this intersection, then the order of that intersection is going to be zero because there's nothing there. All right, so by contrast, if events A and C were not mutually exclusive, if they were not disjoint, then they would have an intersection. They would have some outcomes in common. And so because events A and C overlap, then their intersection would not be empty. Their intersection would be composed of something that they share in common. And so therefore, the order of that intersection would not be zero. It'd be like one if they had one thing in common, or two if they had two things in common. So maybe another way to look at this would just be to look at two people. And so if we had, person number one, and here is person number two, and person number one liked to ski, and person number two liked to swim. Okay, those are each attributes of each person, but there's no overlap there. But if both person number one and person number two liked statistics, okay, now that is something that they have in common. And so if you were to look at the order, let's see, let me back up. So instead, if we were going to look and see if maybe these two people were compatible, we would say that if we took person number one and intersected their interests with person number two, that they both like statistics. Statistics is in the intersection of the interests of those two people. And if we were to completely fill this out, and let's say the only thing that person one and person two had in common is they both liked statistics, then the order of the interests of person one that intersect with the interests of person two, the order of that would be one, because they only have one thing in common. There's only one thing in the intersection between the interests of person one and the interests of person two. Okay. Okay. So this is kind of giving, I would say I started with more of an abstract definition, giving a more visual, concrete demonstration of that definition, and then gave you maybe an even more concrete example with something that's a little bit more personally relatable. Okay, so maybe that helped you understand this concept of being two events being mutually exclusive or non-mutually exclusive, being disjoint or not disjoint. Now let's carry that understanding over to a more numerical example. So here we've got two examples. The first example is showing where two events are disjoint. I like to use disjoint just because it's a shorter word, okay? And so you can see here, A and C are disjoint in the Venn diagram. So A has the elements or the outcomes 1 and 2 in it, and C has the outcomes 4, 5, and 6. And if you weren't looking at the Venn diagram at all, you would see that there are no outcomes in A that are also in C and vice versa. And so the visual representation of that is you can see that event A has the outcomes 1 and 2, and event C has the outcomes 4, 5, and 6. And guess what? Outcome number 3 is in neither of those two. Okay, but events A and C and the outcome of 3, okay, which is not in either, all of them are contained within our sample space. Okay, it's kind of a property of events. They all have to be contained within the sample space. All right, so if we're going to calculate the probabilities, what's the probability of event A occurring? Well, it's the equation for the probability of a single event. The order of event A divided by the order of the sample space. So the order of A means how many elements, how many outcomes are in A. And we can see that the order of A is 2. There are 2 outcomes in event A. 1, 2. For the sample space, what's the order of the sample space? Well, the order of the sample space is equal to 6. And 2 divided by 6 can be rounded down to 1/3. So the probability of A occurring is 1/3. And likewise, the probability of C occurring is going to be 3/6 or 1/2. Now, what's the probability of the intersection between A and C? So this is going to be the order of the intersection divided by the sample space. Let me use a different color. And so what's going to be the order of the intersection? Well, because they don't overlap, there's going to be 0 elements in their intersection. And what's the order of the sample space? It's still 6. What's 0 divided by 6? 0. So because A and C don't overlap, there's absolutely no probability that you're going to get the intersection of those two. All right, by contrast, let's look at an example of 2 non-disjoint events, A and C. Now, A and C, here's A, and here's C. But notice as we look at this list, they actually already have a couple of outcomes in common. A has outcome 2 and 3, and C also has outcome 2 and 3. So we can see just by looking at the definition of these two that 2 and 3 are going to be in the intersection where the two events overlap each other. And so I've drawn the Venn diagram to show this. So in green, we have event A, which includes outcomes 1, 2, and 3. And C is defined to include events 2, 3, 4, and 5. And what is in the intersection of A and C? It's 2 and 3. So you can see that 2 and 3, are in that region of space where the two events overlap. So let's look at calculating the probabilities of A and C. So the probability of A is the order of A over the order of the sample space. How many outcomes do we have in A? We've got 3. The sample space has 6, so that reduces down to 1/2. The probability of C is the order of event C over the order of the sample space. How many outcomes do we have in event C? We've got 4. Sample space is unchanged at 6, so that reduces down to 2/3. So the probability of event C occurring is 2/3. But now, how about the probability of the intersection of A and C? Well, that's going to be the order of the intersection divided by the order of the sample space. So how many outcomes do we have in the intersection? We've got 2. Order of the sample space is 6. That reduces down to 1/3. So this is how we can calculate the probability of not just a single event occurring, but multiple events occurring at the same time. All right. So that ends this explanation for the definition of mutually exclusive or disjoint events. Let me know if you have any questions.